Welcome, everyone. Okay, let's just dive right into this. If you're prepping for your CBSE Class 10 AI board exams, well, you're in exactly the right place. You can consider this explainer your ultimate, comprehensive study guide for Unit 3, Chapter 7. Yep, we're talking about natural language processing, or NLP. We're going to break down the absolutely fascinating world of how we actually teach machines to understand the messy, beautiful thing that is human language.
Here's our agenda for today's explainer. We've got 6 parts: the NLP blueprint, applications in smart chatbots, challenges like syntax versus semantics, the text normalization pipeline, evaluation where we get numbers from words, and finally, some essential rapid revision Q&A. Let's get to it.
Section 1, the NLP blueprint. So what exactly is NLP, and why does it even matter? Simply put, it's the critical bridge between human communication and machine understanding. It's kind of like a giant puzzle. Branching out from this central idea are the 4 core pillars you really need to know for your exam. First, the real-world applications, things like sentiment analysis and summarization. Second, chatbots. Third, the text normalization pipeline. That's how we clean up our text. And finally, feature extraction, which is literally how we turn that cleaned-up text into usable data for a computer.
Section 2, Applications and Smart Chatbots.
Okay, so how is NLP actually used in the real world around us? Well, one of the most common applications you've probably used yourself is chatbots. But, not all bots are created equal. We basically have 2 types. On one side, we have script bots. Think of these as those super frustrating customer service bots that make you press 1 for yes and 2 for no. They rely on really rigid rules and predetermined paths. But on the flip side, we have smart bots. These are the real game changers because they're powered by machine learning. They're adaptable, context-aware, and they actually learn from their interactions with you to provide much better, far more human-like responses.
Section 3, Challenges, Syntax versus Semantics.
Now, you might be wondering, why is human language so incredibly hard for machines to grasp in the first place? Well, take a look at this famous quote by linguist Noam Chomsky: "Colorless green ideas sleep furiously." Grammatically or syntactically, this sentence is absolutely perfect. It's got an adjective, a noun, a verb, and an adverb. But semantically, when we look at the actual meaning, it means absolutely nothing. Ideas can't be green, green can't be colorless, and ideas definitely don't sleep furiously. This right here is the ultimate challenge for NLP, teaching a machine the massive difference between strict grammar rules and actual contextual meaning.
Let's see how a machine actually tackles this in real life. Imagine you ask a smart speaker for the weather. First up, it uses speech-to-text to hear you. Second, it runs that text through a normalization pipeline to clean it up. Third, and hey, here is where semantics actually comes in, it extracts your true intent. Fourth, it retrieves the weather data. And finally, step 5, it uses text-to-speech to tell you to, grab an umbrella. It's just an incredible journey from human voice to data and all the way back to voice.
Section 4, the text normalization pipeline.
All right, this is the core technical framework you absolutely need to memorize for the exam. This is how we clean up messy human text so a machine can actually digest it. Here is the chronological step-by-step pipeline. Step 1, sentence segmentation, breaking a large paragraph into individual sentences. Step 2, tokenization, chopping those sentences into individual words or tokens. Step 3, removing stop words, basically tossing out fluff words like is or the. And finally, step 4, reducing words to their base form using either stemming or lemmatization.
So the absolutely crucial point here is understanding the difference between those last 2. Stemming is kind of like a blunt axe. It clumsily chops the end off a word. So the word caring just gets chopped into car, which totally changes the meaning, right? Lemmatization, on the other hand, is like a really smart dictionary lookup. It gracefully transforms caring into its true root word, care. Now, lemmatization does take a bit more processing power, but it is vastly more accurate.
Section 5, Evaluation, Numbers from Words.
After that normalization process, we have all these clean words. But machines still only understand math, right? We solve this using feature extraction, specifically the bag of words model. We take our entire vocabulary and make them columns. We take our documents or sentences and make them rows. Then, we simply count how many times each word appears in each document. And just like that, boom, abstract text officially becomes rows and columns of usable mathematical data.
But, just counting words isn't always enough, which is exactly why we use TF-IDF, or term frequency multiplied by inverse document frequency. I know, it sounds super complex, but it's really just a calculation that balances things out. It rewards words that appear often in one specific document, but it penalizes common words that appear everywhere across your entire dataset. Basically, it highlights the rare, highly meaningful words so the machine knows what's actually important.
Section 6. Essential Rapid Revision Q&A.
Okay, we've built the foundation. Now let's lock it all in with some rapid-fire revision to simulate those CBSE exam conditions. First up, corpus. What is it? It's simply the entire collected data set of text documents you're using to train your natural language processing model. Basically, it's your machine's reading material.
Next, tokenization. Like we talked about in the pipeline, this is the process of breaking down a sentence into its smallest individual units. Usually, those are individual words, which we call tokens.
Then we have stop words. These are your fluff words. You know, words like is, and the. They glue our sentences together, for sure, but they carry minimal semantic meaning. So we remove them to optimize machine performance and save precious processing time.
Don't forget limmatization. Remember the dictionary analogy? This is the smart way of reducing words to their meaningful base or dictionary root form, which is officially known as a lemma.
And finally, bag of words, or BOW. This is the model that represents text purely based on the frequency of words. It literally tosses the words into a metaphorical bag, completely ignoring grammar, syntax, and word order.
Now for some high-yield board concepts. If you're asked on the exam about the main challenges in NLP, you want to immediately mention ambiguity, the use of slang and idioms, and most importantly, that massive difference between rigid syntax rules and true, flexible semantic meaning. Hit the nail on the head with those points.
You also need to clearly differentiate the bots. Remember, script bots are rigid and rule-based, while smart bots learn and adapt using machine learning. And if they ask why you prefer lemmatization over stemming, it's because lemmatization returns real, accurate root words from a dictionary, whereas stemming just chops word endings off blindly.
And to wrap up our core metrics, a document vector table is that grid mapping vocabulary to documents based on word frequency. And TF-IDF is the scoring concept that ensures highly common background words don't accidentally overpower the unique, meaningful words that actually define a document's core topic.
You now have the ultimate blueprint for NLP. But before we totally wrap up this explainer, I want to leave you with a bit of a provocative thought based on everything we've explored today. If machines are rapidly learning to understand our syntax and even starting to grasp our deeper semantics, how long do you think it will be until they can truly understand our sarcasm? Something to think about, right? Keep that in mind as you study. Stay curious, feel confident, and you are absolutely going to ace those AI board exams.